8.4 exponential models. So what I have drawn here is a linear function and an exponential function. And if you can see here written in the blue, I have the constant growth rate, because it's positive in both of them, that a constant growth rate for the linear is equal to a. So we would write in a linear equation, it's the slope. P equals a times t plus p naught. So that would be like y equals mx plus b form. M being slope or the growth rate. And so is the same thing here, a constant growth rate. But in an exponential function, we have a constant relative growth rate, and we're going to call it a too. But in this one, if you notice, because it's an exponential function, our equation is p equals p naught times e raised to the at. Our growth rate is a in the exponent affected by time as we move along the graph. So this is the same thing. It's a constant relative growth rate, A, that is positive. So what we're going to do here is we're going to say we have a differential equation, and if I was originally to write it this way, I would say this is a differential equation where k is greater than 0 and is our constant growth rate. But for the sake of what we want to do here, I'm going to change that prime notation into the dy dt notation. And then what I'm going to do is I'm going to go ahead and find the solution to this differential equation by taking the antiderivative. So if I take the antiderivative of both sides, and I can't, did that too soon, sorry, hold on. What I would do is then I have to separate the variables. So I'm going to go ahead and multiply both sides by dt, and then I'm going to divide both sides by the y. Okay, now I have the separable. But in this case, I now have this k. Remember, k is the constant growth rate. And in this case, I'm going to temporarily get rid of it so that I can see it a little bit easier in how to find the solution to the differential equation. Now I take the antiderivative, and I can get ln of the absolute value of y is equal to, and then I'm going to have on this side of the equation t plus my arbitrary constant. So then how do I solve for y? I'm solving for the differential equation. I have to solve for y. So I'm going to exponentiate the problem by having the each side become the exponent of e. I'm exponentiating it. So now then e raised to the ln undoes itself and I just get the absolute value of y. And then what do I do with this sum in the exponent? Well, remember, when you multiply like bases, you're really going ahead and adding the exponents. So in this case, I'm going to go ahead and do this in reverse. I'm going to say e to the t times e to the c. But then we have to look at this. E to the c is just a number. And we're going to say this is then our constant coefficient c. And I'm going to rewrite this one more time as this. So that we can then say, here's our exponential model. I'm going to replace c with y naught so that an exponential growth is described by the function in this form. And then we can say that we have that constant growth rate k in the exponent. The initial value of y when t equals 0 is y naught. So if we were going to start with, that's the rate of constant is k greater than 0. It determines the rate of growth, and it's characterized by a relative growth rate. So I want to do a couple of problems. In this problem, they want us to find the general solution of the following equations and express the solution explicitly as a function of the independent variable. So what I want to go ahead and do with this one, and this is not number 9 in our textbook. Oh, that's because I'm on the wrong page, that's why. Let's try this again. Number 9 says, the two functions f and g are given. show the growth rate of the linear function is constant and the relative growth rate of the exponential function is constant. So they gave us two functions. We need to find and show the relative growth rates. So here I'm going to take the derivative of f, and when I do that, I get it's 10.5. And then if I take the derivative of g, I still get an e in the equation. So what I'm going to go back to for this one, to find the growth rate, or k, I'm going to start back with this original equation for the differential equation of the constant growth rate k, and I'm going to solve for k. So I'm going to go ahead and divide both sides by y. And this is what I'm going to be looking for in order to find my constant growth rate of the g function. So that when I go ahead and do this, I'm going to go ahead and take the derivative of my g of t here, and it should be 100 e to the t divided by 10. Don't forget chain rule means divide this by 10 because I'm really multiplying by 1/10. So I'm going to go ahead and change this and say that's really 10. So that is now my y prime in a sense, and I need to go ahead and divide by the y, or I'm going to go ahead and take this in order to solve for the k. I'm going to go ahead and take this and divide by my original function. So I found the derivative. I'm trying to find the growth rate k. So now I have that the derivative divided by the original function, and then I'm going to simplify for k. So I'm going to come down here a little bit and say k is equal to, and it just looks like the e is reduced to 1, and 10 divided by 100 is 1/10. So I do find a constant for a linear equation and an exponential equation, and these are our answers. Okay, I want to go ahead and do number 12. And number 12, it says to us that the population of Clark County, Nevada was 2 million in 2013. Assuming an annual growth rate of 4.5% per year, what will the county population be in 2020? So what I'm going to go ahead and do is I'm going to put that information down. It was 2 million in 2013. We had a rate of 4.5% per year, and we want to know what it's going to be in 2020. So I'm going to go ahead and use this equation, and I'm going to keep it in terms of millions. I'm going to say e raised to the 2 million times e raised to the kt. But in this point, I have to find what k is in order then to solve for t, and I can plug in what we had to find what 2020 would be. So trying to find k, I have to think about this. Because it's a growth rate, I want to go ahead and say, well, wait a minute. When it's 1 year later and I'm trying to evaluate it, we could say y 1 year later should be the interest rate plus 1. We want to increase. So it's always going to be that 1 plus the rate. So we should have 1.045. So the 1 plus. And then this is going to be times my initial amount. And then if I wanted to then, I can go ahead and we'll say, well, wait a minute. If I wanted to set this equal to the y naught e to the kt, but in this case, time is going to be 1. So I don't need the t. If I wanted then, I divide both sides by y naught, and I'm left with this equation. And how do I solve? I'm going to take the natural log of both sides. and this is equal to my k. So then I'm going to go ahead back to my original equation here, and I'm going to put in my constant k, which is ln of 1.045 t. And now I'm going to go ahead and use this equation, and I'm going to try to find what it would be when the time is at 2020. So my t in this case is going to be, or 7 years. So I'm going to plug in 7 to my equation and chug. So P of 7 into my equation. So 2.722 million in population. Talking about doubling time, we want to go ahead and it just gives us that t sub 2 is equal to ln 2 divided by k. And really what it means, if we're doubling our initial amount, we're going to have 2 times the y naught. And then I have this equation, and they're solving for t is what they're doing. They divided both sides by y naught, and we're left with this. And then we take the natural log of both sides so that we get this, and they divide by k. So we have that time is going to be ln of 2 divided by k, and they're calling this with a capital T sub 2 for doubling. And then you can go ahead and use any equation that you need to real quickly. If you need to find t, or if they give you t and you need to find k, it is quite easy to use this equation then to go ahead and solve your exponential problem. So that also then leads us to decay functions, and what the only difference between the growth and a decay is the negative in the exponent to e. And then if we were to try to find a half-life for k, and it's usually what we do for half-lives, it's the same situation. We want half of the initial amount, and they're solving for t. So I'll do that really quick. I'm going to divide both sides by y naught. I'm going to take the natural log of both sides. And since I see a negative, I don't like that. So I'm going to change my left-hand side and say it's really ln of 2 to the negative 1 exponent. And we know the power rule says you can bring that exponent down in front as a factor. So I'm going to have a negative 1 times ln of 2. So that when I go to divide through by negative k in order to solve for t, I now get that t is equal to ln of 2 divided by k again. So this is the same thing as doubling that I can use for half-time or half-life, or the decaying too. But this they're going to be calling t to the 1/2 for half-life. I'm sorry, sub 1/2 to the half for the half-life. So you can go ahead and also then do this in some of your exponential problems.